So the next talk is the talk on LibreSilicon, project that's meant to create a free and open silicon manufacturing process. And our speakers today are Leviathan, ChipForge, and Andreas Westervik, creators of LibreSilicon. So let's give them a warm round of applause. And please welcome them.
Works. Okay. That's probably that's what essentially is all this talk about, is actually a description of what this wafer means and where we will go with it. And yeah, I give now already over to Hagen, which already starts elaborating on the basic conceptual things. Oh.
Okay, hello everybody. Hope you have a fresh mind. It could be heavy. Okay, let's start. What we are. Last year, David was involved at the project to looking for free silicon, just a way to manufacture his own chips, and figured out it's difficult. You need a lot of contracts for that, NDAs, non-disclosure agreements. So he looked around and found a clean room. We had to come in and say, okay, we can rent it. Then he entered the scene on the last Congress, a lightning talk, and said, I like to do that. And I wasn't in the auditorium there, but a guy told me later, okay, look at this lightning talk. It's very interesting. You're already doing chips. So I entered in, seen the talk, recording, and said, nice idea. I will do that too. And now the whole year, we meet us by Mumble. It's just to think of distance, you know. David is located in Hong Kong. The clean room is there. And I worked from Germany. So we exchanging emails. We talked on a mailing list. We built up a small community for that. And we had a first hackathon just to figure it out what we are doing with the tools, which tools are available, how we can use them. Are they usable at all or not? And this was in May. And during the process, the group rised up, and already two of us get the qualification to enter the clean room. The Hong Kong University is a little bit strict in that. You have to sitting there in the courses, you have to do exams. And if you are fine with the exam, then you get the permissions to go in. So Victor, which is on the most left, and David are the both guys. They have the qualification for that, and they they manufacture our wafer, which you have seen there. It's a small one, but it's the first stuff we have, right? Okay, the basic points, what we are doing. We are using a quite, let's say, old technologies from the 80s. It's 1 micrometer feature size. It means the gate length of the transistor has 1 micron. It's not comparable with all the processors you can buy now. It's quite old. It's really stuff from the 80s. But we do it on a new way. We don't use the technology from the 80s. We do it with the knowledge and all the experience from newer technology, doing it again, and using some steps which are not so common, or wasn't common in the 80s. So why one micron? 1 micron also means that the transistors are very robust against 5 volt. 5 volt was the usual supply voltage in the 80s, 90s, or something like that. Now the supply voltage is going down to less than 1 volt. But for tinkerer, for hobbyists, for makers, it's a nice value, because all the stuff, many of boards are still working with 5 volts. And we are able to handle this voltage. So we have a twin well process. Usually in the 80s there was just 1 well. Okay, we have to hurry up. We have 3 metal layers, we have interesting additions, and we are suitable for low-tech, ghetto tech, I would say. You can use it without sophisticated equipment. We can analog stuff and so on. And analog stuff means you don't need small structures. Okay, our areas where we have to work on, first the process. It's almost done. We have figured it out, it works, we're measuring, okay. The next stuff, we need the tools. But the tools are also very old and mostly not usable. We have to deal with that stuff. We have to rethink the tooling for that. And we need standard cells. That's my task. Okay, so a couple of words about standard cells. They are very common. Usually, if you have need to translate your Verilog or a VHDL and to bring it on a silicon, you need small gates, NAND gates, OR gates, and so on. But this gates needs a lot of representation. They're combinatorial sequencing. So, okay, these are typical cells. Just a couple of them. But imagine, we need much, much more. And the design goals for the standard cells are we need almost complete possibilities. If you have just a small selection of cells, the netlist becomes huge. And every gate in the netlist also means a dedicated delay. If you have long change, we have a long delay, so that our operating frequency goes down. So if you have a more complex gates, we are better. But doing all this stuff is heavy. But we like to be low power. It means our cells have to be consumption less power than usual. We want to be fast. But yes, of course, it doesn't fit all together. Okay, cell representation. For simulation, we need it. We need it for synthesis. We need it for timing, as you can see everywhere on the slides. And of course, documentation. That's a lot of work. We are a small team. I am the only guy who's dealing with the standard cells. Usually our teams also doing that. So, okay, we need a tool for that, which does all the stuff for us. And this cell generator, I called it popcorn, because I put in some corn and it rised up with the heat. So, okay, we get all the representation. So, usually, currently, I have a tool on the repository, which is Tackle, which does some stuff I need, but not all. But it already seems very ugly. So for me, I like to rewrite it, but I don't figure out currently which language I like to use for that next time. It could be Rust, it could be Scheme or something like that. We need another language for that. So if someone will help, please. But it's the next task if we have the wafer done completely and measured. Okay. That's a link for the repository where you can look at the current status. And there's a wiki where I like to describe why I'm doing what in which way. But yes, we have to do it a lot. Still more. Okay.
Okay, hi. I take a look at the current tooling that exists, like layouting, place and route to minimize the yield on the wafer. And obviously, because this is a LibreSilicon project, we look at open source tools. So we have Yosys and Graywolf, QRouter, and several other FPGA routers that exist. uses is pretty good. We can probably use this for the synthesis, but the other tools, they lack very critical qualities for silicon, because for example, they are part of Qflow, which is an FPGA workflow. So the Greywolf tool, it originates in academia. It's like it's many decades old. It comes with some very good ideas. For example, simulated annealing, which is a meta-heuristic you can use to solve NP-hard problems, but it's only one of the many choices you can make to solve the extra hard problems. But it also comes with bad implementation. For example, inline syscalls is a very bad idea. It's also written in C and blah blah. Okay. QRouter is actually it's pretty good. It started in 2011 by Tim Edwards. It's widely used by hobbyists and enthusiasts to route for FPGAs, but it's not ready for silicon, and it's especially not ready for our LibreSilicon process, which would require us to write a lot of C code for QRouter. Also, parallelism apparently is not in scope. So, I mean, if we want to scale up, for example, place and route in the cloud or whatever, or use modern CPU architectures, we are stuck with sequential routing, which is pretty bad. Also, it lacks a very important aspect, in my opinion, which is formal correctness. So when we produce wafers in the fab, we want to make sure that they don't blow up in our faces. This is why we need some form of proof that our algorithms are correct, and therefore the result is correct. There are also other productive tools that are proprietary, where we can look at, but we cannot use it or fork it or whatever, but we can learn from the research that has been done. For example, BonRoute. BonRoute is used by IBM. The Cadence suite, I believe, is used by Intel, and the Alliance tools is French academia. Very Unixy. I mean, it has it's a very large set of small tools that convert different file formats to another. I mean, maybe you encountered this problem before when you did some hardware design. You have many different file formats that all don't play together very well. So you have tools like X to Y, which convert file format X to Y. And you see, when you want to place and route and lay out a very, very large chip, like very large silicon integration, then this isn't even done like automatically by tools. This is done with manpower when you look at a very large chip done by Intel or IBM. So this is an example of a very, very large chip. As you can see, I mean, do you think this has been done by automation, like Industry 5.0? No. This is all manpower, and a lot of manpower, which we don't have in the LibreSilicon project at the moment. So this is the state of the art is like, okay, the manpower thing is one aspect, but the other thing is so what you do is you do placing and routing at this at different steps at the design process. So you do placing for a very large chip, floor planning, and then you do global routing, which is you can imagine it like routing along a rough chessboard. And after that, you do a very detailed routing where all the different constraints regarding your technology come into play. And so, again, the formal correctness aspect. So you have some imperative algorithm that you cannot prove will blow up. and it's also not a very parallel code. So you're still stuck with the sequential nature of the code, and you have no parallelism. What we propose is to not place and route for large chip, but decompose the large chip into much smaller units, like a component hierarchy or a subcell hierarchy, and then place and route the small chips at the same time, and then reuse the small units in larger units. So you get an evaluation tree you can work on and compile just the components you need. Also, we propose satisfiability modulo theory solvers. So we can have some first order logic where we can have constraints on the components, how they are placed. For example, they must not overlap. That's like the most simple example. I will show you later. And also, we want to achieve parallel or declarative code. So as you can see, we have many disagreements with academia and industry, which work very well together. For example, when you want to study semiconductor design, you have to sign some NDAs with IBM or Intel to do that. They say placement and routing or floor planning and routing are different problems, and they need to be solved at different times in the process. And then all the components, it can be registers or NAND gates, it doesn't matter, they're all treated the same. It only matters that the floor planning is done first, and then the routing, the global routing, then the detailed routing. What we propose is that place and route is actually the same problem, and that registers are different from full adders. Okay, so the geographical partitioning of a wafer is called floor planning, or the placing step. And this results in a cut tree. So this is how they do routing hierarchies. They just divide the wafer into smaller pieces and then do the following steps based on this placement. What we want to do is have subcell hierarchies, and those subcells, they are either explicit, like they are explicitly developed. For example, the rocket ship is very modular, and it has many explicit Verilog modules you can use and place and route that and then reuse it. And it also has implicit subcells, like for example, most of the time, for example, you have a full adder. It obviously is composed of 1-bit adders, so you can place and route a 1-bit adder, and then place and route based on the 1-bit adders that you already placed and routed, and as a result you get a full adder. That's just one example, but I will show you a tree, a few slides. So there you see parallelism is something very important for us. Bonn route allocates a lot of research to have some mathematical model for concurrency and shared memory models. QRouter, which is the open source alternative, has none. I mean, it's apparently not in scope. And what I propose for the LibreSilicon compiler is the map and reduce approach. As I've mentioned, you get explicit subcell hierarchies through high modularization. This is done by the developers. And you also get implicit subcell hierarchies by compression-like algorithms that X-line, as opposed to inline, the registers or 1-bit adders. And this is also about preserving these newfound hierarchies in the compiler interfaces, so you don't end up inlining them again, because this is not a von Neumann architecture where it would make sense to inline a lot of code, so the code runs on the stack in the level 1 cache. This is about reusing components. Okay, so this is a part of the rocket ship. The system bus is one component of a very modular chip, rocket ship. And as you can see, it is composed of several simple lazy modules, and those simple modules are again composed of other components, and then you have a lot of queues, and this number on the left says how many times it's been used. For example, Q15 is used 5 times in the AXI file for deinterleaver. And this is only the explicit hierarchy that is declared by the developer. Okay. Now, when you apply some compression-like algorithms, you can actually gain, you can get more leaves, so you can be even more modular. For example, Q1 is composed of several implicit modules, and you can see one queue is even reused 7 times. So you just place and route this green leaves like once, and then you can reuse it in the Q1 and everywhere where Q1 is reused at some other point in the chip. Now I want to state a very simple optimization problem. Like what we need for the process is to have components and wires that connect the components, or nets. And these nets and components are rectilinear geometries. The components shall not overlap, and the nets shall overlap with the respective pins they are supposed to connect. The minimizing goals of this optimization problems is layout area, which is the most critical one because this is what maximizes yield. The maximum wire length, because it's about resistance. The wire count you want to keep very small, but you want to allow for wires. The crossing number is a computational thing. It doesn't really matter for the implementation on the silicon. And you also maybe want to minimize wire jogs, which is bends in the wire. So to solve optimization problems in 2018, maybe you want to use an abstraction from the SAT solvers you used to know. Academia came up with some pretty neat theories called satisfiability modulo theories. And you can just put some first order logic and give it to a solver. For example, I've listed a few. For example, ABC is used by Yosis, and Z3 from Microsoft is also a very promising product. But you can obviously choose from many products by academia and industry. Just a quick reminder what Boolean satisfiability is. Find assignments for all these 6 variables, which are Boolean, so that the whole term is true. And now with SMT, or satisfiability modulo theories, you can do the same thing, but now with integers and also more complex data types, but integers are the most interesting. So let's do something with SMT. For example, let's have a component that is rectangular, and now you can see this is like a Cartesian coordinate system, and you have the left bottom point, which is x and y, and then you have the right and the top point. And now if you for example have this problem that you don't want to have overlapping rectangles, you can have rectangle A and rectangle B, and declare these coordinates, and then have some proposition that shall be true, And to have a proposition that says they shall not overlap is to say this. I mean, it's actually the lower half. That is, the lower half makes sure that they don't overlap, and the upper half makes sure that the components actually have the right dimensions. Well, in this example, they obviously have the same dimensions, the same components, and so you make sure that the left point of the second rectangle is like right of the. Oh, okay, no, never mind. Okay, okay. One last important point I want to make is that this framework we want to create, it's not based on the inheritance model that we've seen in the process steps right now, but we want to combine the problems, for example, the overlapping problem, the pin connect problem, and then arbitrary constraints that come up during the process development that Dave and Hagen will supply me with, and I will formulate that in first order logic, and then this makes sure it's formally correct and it doesn't blow up. And as you can tell, I mean, I've combined many NP-hard problems at the same time, but I think we can manage that if we have very small cells. So I suggest we just stay here and don't do all this for very large chips, but reuse small chips and then reuse the small chips in other small chips. The silicon compiler is one half of maximizing yield, and the other half is to get the process right. So to get the process right, we have David and Victor. So please.
So thanks for the handover here. So very first, there's a lot of questions why Hong Kong. So one thing that this is a really suitable place to do that is because of history. Like the epic Commodore 64 has been made in Hong Kong. Then the chips in the first Macintosh have been made in Hong Kong. And all these manufacturing lines, some of them, at least one, is still available. So also there is a very advanced laboratory. That's the NFF, Nanofabrication Facility in Clearwater Bay. And they let us kindly use their equipment to develop this process. Also, one of these factories I mentioned before, ASIAL Semiconductors, they're really open to introduce LibreSilicon in their mass manufacturing lines. One in Shenzhen, one in Taipo. Yeah, so also in conclusion of that, we have advanced R&D labs there. There is factories available. We can easily export it to here over channels which already exist, right? And also in general, it's just more relaxed over there. I don't like minus degrees. So our process is a little bit of a monster, so it makes sense to tackle that one by one. So we're right now feeling ourselves upwards to get the standard CMOS debugged final with optimized frequencies there, right? But we already have on the Pearl River, I've shown you, we already have test structures for high voltage MOSFETs, B-junction transistors, Zener diodes, even flash, resistors and caps. So, and it's only a question of effort, I guess, in the next few months to get that working, right? When we designed the process, like how it usually works when you make a process is you look at the machines you have available, what can these machines do, optimum operation range, Then you look what substrate, what material you have available, and then you start tinkering your own little proprietary process. That's how fabs do that. And we said, okay, well, to the point where we look at the machines, what can they do? We do the same, but afterwards we looked at it's portable, not specific to the equipment. So just because we have certain machines which can do awesome things, but they're really exotic, doesn't mean we have to use them. So we avoid exotic machines, so that it's as portable as possible. And we also try to use wet etching whenever possible, in order to make sure that you even can build it in a basement. And yeah, Evan Heisenberg might be interested now in you know, changing business into a less dangerous business. And yeah, they even can build it in the Innovation Hub Hamburg, I've seen, like this improvised clean room with just a diffusion furnace. So that's a cross-section of the, it's not final list, but you see a cross-section theoretical. That's, by the way, you can find it on GitHub as well. It's all in the publications. Everything we develop, all the measurement data, all is on GitHub. So that's actually the layout of these little squares here on the wafer. You see the apple in the middle. It's the same as here. It's nice. I have a Python script in the GDS2 generator tool folder for Python, and you can take any PNG or anything and just convert it into layout format. So you can put your own pictures onto the metal-free layer. So in case you already are interested in making little chips or so. It's also possible to make like earrings also with, we don't care as long as you pay the square millimeters on the silicon. You can put pictures on the silicon. So that was the Pearl River, right? And the Pearl River fulfills the function for us at the moment to debug all the features of our process, of this LibreSilicon process. Then the next thing, we have to use it to calibrate new foundries. So now we developed it at NFF in Clearwater Bay, right? And afterwards we go over to HQ to the RCL guys, right, in Taipo, and they have the machines, and then we have to pipe the Pearl River layout through there as well, and repeat that process over and over again until the measurement data, like the you know, the beta depending on omega of the transistors and the resistance of the virus and everything, kind of is the same as at NFF, so that you can basically, as I mentioned before, one of the design concerns is portability, that you can basically prototype a chip at NFF and then produce it in RCL or in maybe some other fab in Shenzhen or whatever. And if there are new features coming out, we just make a new release of the Pearl River MCU, Pearl River test wafer, and we give that around, we push it to GitHub, and people can introduce and calibrate the process to support a new feature. And so that's how does it work. So typically you have something like a photo mask, like here. I didn't bring that one because it's in a clean room there, and the dust might scratch my microstructures on there. So also afterwards I have to clean it for half an hour, and when I come back to Hong Kong from here, I'm so jet lagged, I just want to get started again. I don't want to wait for the mask. But that's a picture. And these masks usually are stepper aligner specific. So if you have a stepper aligner, if you don't have a stepper, then you need to make a direct transfer. That means you actually have to put the chips in the size you want to expose them directly onto the mask, then press the mask onto photoresist, expose, and develop. That's messy because you have to clean the mask all the time, and it really depends. So actually you can do exposure even without a stepper. So you actually really could do it also there in this university lab in Hamburg. So all you need is a new UV light. So we have a little bit more advanced tech in Hong Kong. So we have here an SVG coater. This baby dispenses automatically HPR 500, a resist. So we actually just have to put in the left, you see the cassette slot. So you put there like 25 wafers or so. And then you have a receive slot and put another cassette there. And it just starts sucking in the wafers one by one. Put primer on it, soft bakes it, and easy. Then you expose it, develop it, hard bake it, chilled. We have two types of resist actually, and the 6400L for the implantation unfortunately has to be put in manually. So yeah, it comes and it gives you 10 seconds to open the chamber and put the resist on it. In both cases, however, it doesn't really matter so much because the thickness of the resist is depending on the RPMs of the spin coating unit. So you just have to kind of put 2/3 of the wafer should be somehow covered with the resist, and then you cover, and then you must, and the excess resist goes away. But you have to control the RPMs because depending on how, when you do wet etching, for instance, the HPR 504 has to be enough thick because of selectivity, so that you don't consume, your etchant also consumes the polymer, the resist. So you have to make it enough thick that you don't have consumed all the polymer before you have etched your structures. And the same goes for the implantation, because you can use, for that you need the 6400L. This one can sustain higher temperatures, so you can use an implanter. Thanks. But yeah, scatter. Okay, now afterwards, after exposure development, it looks like that. That's an alignment cross for our optical stepper. And for instance, that's our ring oscillator. So it's one of the structures on our Pearl River, actually. So annual P-well. I have to hurry up, only 10 minutes, so sorry. So that's a picture after developing. We have some P-well mask developed, so you have everywhere resist except in these little crosses and stripes there. That's there below is the silicon where we implant. So the receipt is easy. First coat, expose, implant, and then resist strip. Same for the other, for the P-well. And after the resist strip, you can put it into a diffusion furnace in inert atmosphere for 4 hours. So where does the 4 hours come from? So we have the Fick's equation. And the Fick's equation is essentially in a similar shape like the Laplace heat conduction equation, so there's already nice solutions for it. So for instance, if you use boron and phosphor, which have the nice property that they have the same constants for this dE. So if you have the same temperature, you basically have the same dE for phosphorus and boron. So you can implant them next to each other and then put them at once into the diffusion furnace, and the wells are the same depth. So that's why these two materials are usually used for diffusion. So that's one of the solutions. With that you get the surface the doping for the threshold equation, which I also will rush through in a moment. So yeah. Yeah, that's the equations you see here with background doping. It's a little bit much. You have here this natural logarithm inside, but besides that, you see this jump, and that's how you essentially build a well. You have the background doping, and you compensate donors and acceptors with each other. So that's what this absolute value of the difference means. So the threshold equation is pretty easy, and they are like basically mirrored for PMOS and NMOS. They're just like mirrored in the sense that one of the transistors, so PMOS is built on an N well, and NMOS is built on a P well, right? What essentially controls the threshold voltage, so the operation voltage, which usually in the standard CMOS is around 0.8, respectively minus 0.8, that's the doping here, like the donors, respectively acceptors. And the QSS usually, that's the oxide charge, is usually a process-specific constant, but it can change. In that, and then you get flash. You can change QSS, and then it's flash. That's what you use in Sonos flash. Stands for silicon oxide, nitride oxide, silicon. So there you have a standard, again, MOS, NMOS in this case, but you have a sandwich. Instead of a normal oxide layer, and for the gate oxide you have an oxide, nitride and oxide, and these oxide layers above and below the nitride are called tunnel oxides. And the trick is that with a high enough energy, you tunnel electrons into through the oxide into the nitride where it's trapped, and then you shift the operation voltage, the threshold of the transistor. And when you then put an 1 at it, it doesn't turn on anymore. And that's essentially how the most used flash solution besides normal floating gate works. It's really simple. So, and after you get your wells out of the furnace, so I did a little detour, you want to make sure that the lateral diodes, which got into existence after diffusion, don't create unwanted short circuits. So we use a technology actually developed much later after 1 micron already has been out. It's called STI, shallow trench isolation. It's from the ULSI technology, as well as the silicide we use to reduce the resistance of the polysilicon gates. Here are some pictures. We did etch this one in the lab. That's the islands, so that around everything going down, that's the trenches in between the gates, between the wells. So we isolate them from each other. So the recipe is pretty easy. So either you have a plasma etcher around, or if you are not rich and don't have money to buy a plasma etcher from eBay, you can also get this tetramethylammonium hydroxide. And it's not even a German name, a word, so cool. Diluted with the ionized or deionized water, 3:1, and this 25% TMAH solution. You heat it up to 80 degrees Celsius, dip your wafer for 6 minutes, and then you get your structures. Metal is even easier. So we did here the metal interconnect for the ring oscillator. There, etching it also, you make a vacuum, deposit 100 nanometers aluminum, 30 nanometers titanium for passivation, take the vacuum away, dip it into HF until you don't see streaks from the titanium, then into aluminum etcher until you don't see streaks from the aluminum, and then you have your wires. I skipped that one, that's just really interconnect. But I plan to make videos soon where I go through the, like daily video blog of results. But just that you see the oxide, depending on the angle, it has different colors. So that's LTO, the isolation. And then you see our topological measurement device. You see this 1 micron, because we only deposited 1 micron for now. You see the height differences, and we see that 1 micron is not enough. So we still have these sharp edges, which we don't want. So we have when I'm back in Hong Kong, I have to deposit another 2 microns. And if you want to follow up, you go to my GitHub, okay? So Victor, that's him. And I have done that so far. It's only like 2 weeks because it took a lot of time to get all the masks manufactured, and so a lot of bureaucracy. We already have that much, and just stay tuned. We already have figured out so much in the last 2 weeks that it shouldn't be long before we can, well, finish all the features of Pearl River, create models with Hagen's popcorn, and start figuring out all the analog stuff for our MCU, and then we make an MCU. That's the first thing we want to do as soon as we have the features figured out of Pearl River. If the goddess is nice to us. Yeah, it's Discordia figurine is really cheap on eBay. So yeah, that's like the overall of the features. We want to build this microcontroller. And yes, because the other folks don't believe that there are people who want to buy such MCU, please fill out the survey. Yeah, that one is from Hagen. I skipped that, but yeah. So yeah, thanks. I'm done, and too late, but sorry.
Thank you for the talk. Now that it's too late, we have time for questions. So there are 2 microphones. One is in the middle and one is on the left side of the stage. Line up and we're going to take some questions. And there is already 1 question from microphone number 2.
Okay. Sorry. Thank you for that interesting talk and all the development that you're doing. I was wondering, have you had any time to test your transistors yet? And then later on, do you plan to release some sort of analog simulation capabilities?
Yes, exactly. That's planned for the next few weeks after I'm back in Hong Kong. We will go back into the clean room. We actually wanted to provide already something for the Congress. Unfortunately, we were short noticed, that Thursday and Friday they take the wet stations and the machines offline for maintenance of the AC. So we have already, like the wafer, we have the isolation oxide, but we didn't have any time left to actually test the only having polysilicon is not enough. You have to also have metal to go with probes there. The stuff is micron size.
Okay, your question, as I understand, was in the direction of simulation, right? We like to measure all the structures we have to produce, and with the values we get, we like to feed in SPICE models. So you can do analog simulations. And yes, we like to use this technology for analog stuff. Because as I already mentioned, 1 micron size is enough for analog. You don't need smaller structures. Analog are always having huge transistor size for 20 or 50 microns. So they are huge. You don't need the small technology. So they are quite feasible for analog stuff. But let's say in this way, if you're doing analog stuff in a conventional way, you have to sign all the NDAs, and you're stuck on this technology you're using. You can't transfer your design to the next fab, because in the next fab, the PDK is different. You have transfer or to translate all the structures, you have to rebuild again for the new technology. If you have a technology which you can take from one fab to another, like our one, you are quite happy because the analog stuff you designed once also fits for the next fab. So yes, of course, we like to support analog stuff, we need help for that. Of course, we have to measure. We are currently developing the wafer. We are currently working on the documents, how to measure, what we like to measure, and then we have to transfer the values to SPICE. But we have also document how we are doing that, and so everyone can use the knowledge.
Thank you.
Thank you. Mic 1, please.
Do you have any plans for open source mask production? Like,
yes, actually, the problem is only that, as I mentioned before, if you want to have an opto mask for steppers, that's always manufacturer specific. If you want to have a direct transfer mask, not a problem. So I guess, so Sam is really helpful in the lab. He runs the laser scriber. We could talk with the folks at NFF. They were really lovely, helpful. They really help us a lot. And also now that we talk with RCL, and they also have laser scribers, there we could actually also start producing masks in the long run. So yes, that's certainly one of the things I intend to do, is providing optical masks for exposure. Yeah.
Thank you. One more question from microphone 2.
Hi, yeah, great talk, thanks. I'm really interested in what it would take to build the fab. What's the minimum set of tools? We've already seen a couple of orders of cost reduction in sort of DIY biohacking by making the tooling a lot cheaper. Do you see that happening within the nearest decades in your sort of work?
Yes, so for instance, I made my process by purpose this way that you can actually improvise most of it, like the LTO growing and deposition and everything, with a furnace. So what you need is a wet etcher, like some wet etch station. You can actually, there is a video from Cherry Ellsworth called Making Microchips at Home, Cooking with Cherry. And she does microchips in her kitchen. So it's not, you get scared like HF it dissolves your bones and so on, and then you see the guys who already have are qualified or employed there, they just, without any PPE, nothing, just grab into the HF. It's just to scare folks from generating insurance problems. In general, it's not really that dangerous, right? So you can do the stuff at home, no problem. And yeah, so we intend, this process I made is so trivial. So we have also a branch called super low tech, which has essentially, but that needs more R&D, but you could actually help there, for instance, figure out the last details, get a furnace from eBay, put it into your kitchen table, start R&Ding, make some Git pull requests, and we're super happy. Okay, so it's doable, and the furnace you get on eBay, so it's not so a problem.
Thank you. Microphone 1 again.
Yes, so you just said about the analog stuff that a lot of that is usually under NDA for the fab. So have you encountered any problems with the fab that you're currently using that you're actually trying to discover these processes for yourself? Like you're generating competition that they might not like. Have you had any problems with that?
Oh no, I had nice phone calls, emails with the owner of the fab over in Taipo, who also has a second brand in Shenzhen. That's RCL. I actually asked him recently, hey, is it okay when I use your logo in the presentation and implicitly make advertisement for your fab? And he, no problem, go ahead. Right? So it's like, and he's really eager to, LibreSilicon is what they need, because every fab usually has to invest money to develop, first they develop the proprietary process, right? Or they license some proprietary process from another company. And then they have to invest R&D costs to develop IP cores for their setup. With LibreSilicon, the problem is solved for the companies, because these foundries using LibreSilicon, everything the community develops is on GitHub, and that's that's the IP catalog, essentially. So they don't have to invest any additional money into R&D and IP cores. That's in the nature of open source, that there are IP cores popping into existence all the time. They can focus on the thing they're best at, making silicon, right? So it's actually positive, but only for the small foundries. They're really interested, especially Shenzhen, now some in India and so on. But the big foundries, they will not, the big companies have the tendency to be as mobile as a cargo ship. So it will take at least like 2 years until they haven't acknowledged that LibreSilicon exists. And then we might expect some legal, bullying. But for now, they won't even, they just laugh, right? They just laugh at best. Yeah.
We're going to have 2 more questions before we're out of time. Microphone 2.
Hi. Why did you go for the twin well process as opposed to the simpler single well?
That's a good point. That's also something with portability. If you have different vendor, different supplier for substrate, it might be that's an n-doped or an undoped substrate. So with twin well architecture, and actually we have on the n well we also built p bases, and in these n bases, so we have actually like stacked wells in the n wells and p wells. So actually it's a 1, 2, 3, pentagon well. I don't know. And that's just that you can shift the doping of the N and the P substrate according that you fit LibreSilicon requirements to still have the physical properties ensured by LibreSilicon, no matter whether you get your substrate from somewhere from Great Britain or from Taobao.
Okay, the thing is we looked before at eBay, which wafer we can get. Currently, NFF is supporting us with wafers. But if you're looking on eBay or Alibaba or what else, we get different wafers with different dopations. And if you have something which say, okay, we're just building an annual, we have to verify or lie on the P base, right, or on the P substrate. And to avoid the obstacle, the difficulties we're doing twin wells, we can just regulate our own dopant inside and we are fine. We don't have to rely on the wafer or substrate itself. What was the basic point?
Thank you. And the last question from microphone 2.
Hi. So once you have your complete die, how about packaging and bonding? Because if you want to use it, you have to place it somehow on the PCB.
Yes, so we have a bonding setup at Taipo already. That's what still is being used at the moment in Hong Kong, is the packaging. Then we have some guys in HKSDP with packaging setup. They even can make nice tape reels, and they have also like after packaging tests, like did the bonding work, is it damaged by the bonding, and so on. Hagen and I, we figured out some nice bonding pad design, which didn't fit at all anymore into the talk. I already over-talked like that. But it absorbs the physical stress from bonding. So we think that it's aluminum covered with titanium, so you don't have to sweat away any oxide, right? So you have better bonding capability, better bonding properties. So it shouldn't be such a problem, and we have plenty of bonding and packaging labs which have already promised to help us. So it's really like, it's more like to choose which one we take.
Just an annotation. If you like a dedicated package, please mail us. Right? We are fixed now on the dual inline package. We are thinking about flip chip BGA. But if you have other package which is more common for Tinkerer or something like that, please mail us.
Thank you. Thank you for the talk. That was the talk on LibreSilicon. Leviathan, Chipforge, Andreas Westervik, and Victor. Thank you. Thank you.